Okay, and then go back to a screen share. Um, this one. Okay, are you seeing a screen that says problems, segment 14?
Yes, sir.
Good, okay, all right. Okay, what we're going to do right now is look at actually fairly easy stoichiometry problems. Um, if you've got a reaction such as this one, this is the combustion of a compound called benzene, C6H6, to make carbon dioxide and water. And suppose we're going to know how much heat is involved when 3 moles of benzene react with 12 moles of oxygen. Well, uh, we're going to work it just like we've always worked them. The problem quantity given was 3 moles of benzene and 12 moles of oxygen. So I put those over the formula for the compound, for each compound. And then under that, I want to interpret the balanced equation in the same unit of the substance that's over each substance. So I was given an amount of benzene in moles, and the equation is showing 2 moles. I was given 12 moles of oxygen. The equation is showing 15 moles. So 3 divided by 2 is one of my rebalancing factors. That's 1.5. And 12 divided by 15 is the oxygen rebalancing factor. That's 0.8. So the limiting reagent rebalancing factor is the 0.8. And I'd need to multiply that through the entire equation, including the heat. So if I multiply the rebalancing factor times the negative 4394 kilojoules, that gives me negative 3515 kilojoules would be released or would be involved. I have to be careful about the language here, because if I tell you minus 3515 kilojoules is released, well, the release means it's negative, so minus 3591, 3515 released would be positive. It's the language, so I try to be very, very careful. If I tell you the heat is released, I'm already telling you the sign's negative. And if I tell you it's absorbed, then the sign is positive. If I tell you the 3515 kilojoules is involved in the reaction, then I didn't give you a sign. So what I should have said was minus 3515 kilojoules is involved in the reaction. Okay, enough English. That's for another teacher for another time. Okay, now where does the chemical energy reside? It resides in the chemical bonds that make up a molecule. We can make bonds and break bonds during chemical reaction. That's essentially what we can imagine happening. So essentially we can do a Hess's law type problem where I take all of the reactants and I write out the valence bond structure for each one of them. And then I imagine I'm going to break all those bonds to make gaseous atoms. So I'm breaking all the reactant bonds to form atoms. Then in the second step, I'm going to take all those reactant atoms and rearrange them correctly to create the new bonds in the products. And I'm going to then form those new product molecules from the atoms I generated from that first step. So it's sort of like what we did when we did delta H of reaction is the sum of the delta H formation of products minus the sum of the delta H of formation of reactants. It's sort of the same thing, except in the delta H of formation equations, we're talking about taking molecules and converting them to the the molecules that or the atoms that made it up. And so in this case, we're going to, instead of going to the elements, we're going to go to the atoms. And the advantage is this. For some molecules, say you're a chemist and you make a new molecule. Well, if you've made a new molecule, the heat of formation of it is not known. And so you can't involve it in thermochemical reactions because you don't have the heats of formation. Now you can estimate that by this method that we're looking at now. So here are some typical bonds. Now, just to be informative about how we get this information, way back earlier we talked about a device called a mass spectrometer. And the mass spectrometer measures the mass of ion fragments that are created when we squirt that sample into an ionization chamber. The electrons strike those molecules and knock an electron out of the molecule and leave the molecule as a positive ion. And then that positive ion gets attracted through a negative electric field that's got a hole in it, and then positive ions can shoot out through that hole and then be bent by a magnet according to their mass to charge ratio. The heavy masses don't get bent as much and the light masses get bent more and so forth. Well, what I didn't tell you is that that ionization chamber is so vigorous that it does fragment the molecule too. Not only will it form a molecular ion, but actually the power of the machine is that it breaks the molecule into its probably most stable pieces. So the pieces aren't stable, but some of them will last long enough to get through the mass spectrometer. And so when you shoot a big heavy molecule into the machine, it breaks it up into a bunch of little fragment pieces with certain masses. And that pattern of masses that you see from the mass spectrometer is a fingerprint. And you can take extremely large molecules, shoot them into a mass spectrometer, it breaks them up into a characteristic pattern of little pieces, and they will then hit at different places and produce that characteristic pattern. So every molecule you spray in is going to give you a mass spectrum that is characteristic of that substance. It's one of the most powerful methods we have. And modern machines come with a library of hundreds of thousands of molecular fragment patterns in it. And you can spray something you don't know what it is. You can spray that into the machine and it'll give you the most likely compound that was in that sample. And you can analyze for known things like the state crime lab. That's how they detect different kinds of drugs in samples that they've collected at crime scenes. They can get that pattern. Well, one of the things that happens in the pattern is you might break off an atom. When you break that atom off, you've broken a bond. And so the mass spectrometer can tell you how much energy it took to break that bond. And here are some listings of some of them. An OH bond costs about 464 kilojoules for 1 mole. So if you've got an OH bond in a molecule and you want to fragment that to an oxygen atom and a hydrogen atom, it'll cost 464 kilojoules per mole to do that. An oxygen to oxygen single bond is 142. That's not a very stable molecule. It's a peroxide. And so you get that kind of energy. Carbon-hydrogen bonds is a good deal stronger. And it gives you, you require 414 kilojoules per mole to break that. And so here's a listing of some of them. I don't have, I have one double bond on there, and it's at 502 for oxygen, gaseous oxygen. And I told you the nitrogen to nitrogen triple bond is one of the strongest we know. It's 945 kilojoules per mole. So you see it's almost twice as much as that double bond. Not quite, but almost. And a lot more than most of the single bonds. Now, what I'm showing you here, if I took water, for example, it would have two OH bonds in it, one to each of the hydrogens. And the breaking of that first bond in water to make a hydrogen atom and an OH would be, I don't know, some number. And then the breaking of the second bond would be a different number to make the second hydrogen atom and release the oxygen atom. And maybe the average of those two would be 464. Well, we don't only have OH molecules in water. We've got OH molecules in alcohols. All different alcohols have an OH bond in them. And each different alcohol would have a slightly different strength for its OH bond. And all organic acids have an OH bond. All the weak acids we've studied have an OH bond in them. And their energies will actually be pretty small, really. But that's part of the types of OH bonds. So when I write 464 here, that's not the energy of any single OH bond. It's the average of all the ones they've measured. And so when we do heats of reaction, as I'm going to show you in a minute, we're not going to get the exact value. What we're going to get is what we expect from the average values of all the bonds. Now, here's what we're doing. We're going to break all the reactant bonds and form gaseous atoms from them. And then we're going to take those gaseous atoms and reform the products out of those. Now, can we really go that way? No, we can't do that chemically any more than we could take the heats of formation of reactants and make elements out of them. We can't do that either. But remember, energy only depends on the initial state and the final state, not how you got from one place to the other. So this is going to be another way to go from reactants to products that involves breaking bonds. Now here's an example, the chlorination of methane. It's a common reaction. It's done quite often industrially. And what we're going to do is we're going to replace one of the hydrogens with a chlorine, and that hydrogen will attach to the chlorine to make HCl gas. And that reaction can go. We can figure out the energy of the reaction because I'm going to break all of these bonds. There's 4 CH bonds. They were worth 414 kilojoules per mole, and 4 moles of them. We got the energy to break the methane up into its atoms. The energy required to break chlorine into its atoms is one of the CCl bonds, which was 243. Now, if we look at what's formed, we're forming 1, 2, 3 CH bonds over here. So that's going to be 3 times 414 kilojoules is the energy involved in these 3 bonds here. Then we've got an H and a Cl bond that we formed, and that's 431 kilojoules per mole. And then we've got a CCl bond that was formed, and that's 331. So if you add up all of the energies of the broken bonds and all the energies of the product bonds with their correct algebraic sign. Now, here is an important point. If you're breaking a bond, that takes energy to do that. When you form bonds, that gives off energy. So all of these broken bonds should be a positive sign, and all of these formed bonds should be negative. And so we combine the two and we get minus 105 kilojoules as the expected energy for this reaction. So you see, by looking at taking that table of bond strengths, they're called bond dissociation energies. If we take that table and calculate the amount of energy involved in breaking the bonds, the amount of energy involved in forming all the new bonds, we can then estimate the delta H for the reaction. The actual value, if you use the heat of formation of products minus reactants, or measure it in a lab, it's minus 119. So you see, we got a ballpark figure, but not the exact figure. And that's what you expect. But sometimes that's good enough if you can't do it any other way. If you're a chemist and you've made a compound that you think is the only sample of that compound in the whole world, you've got a pretty good idea of what its bond structure looks like. And you can figure out what kind of bonds it's got in it, and you can figure out what you expect the heat of formation of that compound to be. And then you could use that in thermochemical reactions from this estimate you made using bond dissociation energies. So this is an easy way to do it. Now, this is the slide we've been looking for all summer. We've just finished the course, and may God bless you and keep you, and may he make his face to shine upon you and give you peace. May your dreams come true and your plans for the future come to pass. And I know you've all got, you know, I really do enjoy working with young people because you're at a stage where you've got so many hopes and dreams for the future. And, you know, if you focused on those the way you are right now, you didn't have to come to college. You could have gone out and done something different, but you chose a harder route. And someday that's going to pay off for you. It's going to lead you to a wonderful life. And I hope along the way that you'll kind of think back on how you got there and the opportunities that came to you. You know, there is a plan for your life, and I hope you fulfill it, because that is the route to true happiness for you. It's not how much money you make, and it's not how many friends you've got. It's not how important you are or how many people know your name. It's how close you come to fulfilling the destiny that was prepared for you. And so that's the end of the lecture. So let's stop the recording and recording like that. And now I can go back to screen share, which was this one. Okay, all right. And the first one, okay. I'll have to switch back and forth. So for number one, now tell me what you're seeing. You're just seeing the exam, or do you see a little thumbnail of my camera over here? Do you see that?
Just the exam.
Just the exam. Okay. All right. So I do have to switch back and forth. Okay. So we got calcium hydroxide, and you are going to have to know what the formula is. Well, the hydroxide ion is OH minus. So so you've got OH, it's a -1. Calcium's in group 2, it's +2. So the formula is going to be CaOH2. You're going to need that. And I need to make this smaller so I could sort of see both. Okay. Okay. All right. And it says we've got 1.85 grams of the solute, and it's in 100 milliliters of the solution. And it asks what is the molarity of the saturated solution. When it asks for what is the molarity, we've got to know we need the number of moles of the solute, and we need to divide that by the number of liters of the solution. Okay, now, number of moles, we got to get that. So the number of moles is going to be equal to the mass, 1.85 grams, divided by the molar mass. Calcium is 40. Let's see, I better get that out where I can see my periodic table. I keep telling myself I'm going to print one out that's bigger, easier to read for me. Okay, about 40.08 if I want to be 2 decimal, 4 significant figures. So let's do it, 40.08. Plus, I've got 2 oxygens. That's 2 times 16. And I've got 2 hydrogens. That's 2 times 1.008. Well, 1.00 is close enough, I think. Okay, now, so we can calculate the number of moles. 1.85 divided by, left parenthesis, 40.08 plus 2 times 16 plus 2 times 1.008 is the other digits if I wanted it. Okay, I've punched my calculator, and this is going to come out to be 0.024 967. Now I want you to notice something right there. Look at, I have to screen share to show it to you. Look at response B. That's the wrong answer because we got moles instead of molarity. So the molarity is going to be this number of moles divided by the volume. And if you're looking at the problem now, the volume is 100 milliliters. So let's stop the share. So I've got that number of moles divided by 100 times 10 to the minus 3, 100 milliliters. This would be moles. Okay, so I've got this number for moles on my screen. I just need to divide it by 100 with an exponent of minus 3. And I come out with the real correct answer, 0.250 instead of 0.0250. So that is the correct answer. That comes out to be, I guess it's C on the test question. Now, the point there, you can move the decimal place. And, you know, if you're comfortable doing that, okay. But you do run the risk of always going the wrong direction. So that's why I wrote 100 times 10 to the minus 3, because the problem said 100 milliliters, and I needed liters. So I just replaced milli with what it's equal to, and I entered it like that on my calculator. Your calculator will take 100 exponent negative 3, just as well as it will any other number. All right, so let's see. I'm not seeing the screen share, so I'm not sure that I'm, okay. Let's go back here. Okay, now I think you're looking at the quiz or the exam. And now, if we looking at number 2 is what mass of uranium in milligrams is contained in 1 milliliter of 4.55 molar uranyl phosphate solution. Okay, so our compound is getting things so I can see it a little better. Okay, now, okay. Okay. Yes. Oh, we already saw that. You don't need to see that now. You need to see the solution. Okay, here we go. Okay, we've got 1 milliliter of 4.55 molar, and it's uranyl UO2, and that looks like a 3, PO4, and I thought I had more paper room than I got. It's PO4 3. Okay, I'll pull it over where we can see it a little better. So we want to know the mass the mass of uranium in that contained in 1 milliliter of that solution, and we wanted it in milligrams. Now, I want to show you if I had milligrams per milliliter. That's what we want, right? That's the millis would cancel. That's going to be the same thing as the grams per liter. And that's easier to calculate and less likely to make a mistake. So suppose I had 1 liter of that solution. If I had 1 liter, then what would I have? I would have 4.55 moles in 1 liter of that compound. Okay. I don't know why I did a 3 and I did. Okay. All right. Now I have 1 mole of that compound. So what I want to know is how many grams of uranium would that be? So 4.55 moles of UO2, 3, PO4, 3. And now I want to go from moles of that stuff. I'm just going to put moles of that big old compound in here. And I want grams of uranium. How many grams of uranium is in a mole of that? Well, it's 3 moles, so it's 3 times the molecular weight is 238. I think 0.03, if I want all the digits. Yeah, that's right. Okay, so I can do that math. So that's then kind of simple. 4.55 times 3 times 238.03. That should give me my answer. And I get 3250. And that would be grams per liter or milligrams per milliliter. It's the same thing. So I'm going to go through that to show you that if you've got these prefixes, they are just like variables. They'll cancel out. If I got an M here and something here and an M here and something there, the M's going to cancel. And since molarity is defined in moles per liter, it's easier to calculate moles and liters as the units in a problem if you can do that. And so I'm usually going to do that even if I have to do, in this case, they were the same. So I got the answer as soon as I got this one. But in some cases, it's easier to get this one and then convert to some other unit if that's what you needed. So that's a fairly decent problem, not bad. Okay, now let's look at the next one. Oh, there's what I wanted a while ago. All right, that makes it easier. And so now I've got it formatted so it won't look messy when we start working with the problems. And I'm going to pull the view up a little bigger now that I've got control over it. All right. Make it easier for you to read too. Okay, maybe a little bit more right there. That should cover everything. All right. Now we're dealing with a stock solution of perchloric acid is 75% perchloric acid, has a density of 1.67 grams per liter. What is the molarity of the solution? So all right, now it's 75.5% perchloric acid. So perchloric acid comes from perchlorate ion. Perchlorate ion is ClO4 minus, so I'll need a hydrogen. So the compound is HClO4. Now, just as I promised you way back in the beginning when we started nomenclature, I told you by the time we get to here, I'm going to be giving you formulas and not names. If you don't know that that's HClO4, you think it's HClO3 or some other formula, you're going to miss this problem. There's no way to get it without knowing that formula. So if you need to brush up on formulas, do that again, how to take formulas to names and names to formulas, because that's going to be very critical. Also, the other piece of information we know is the density is 1.67 grams per milliliter. Now, it asks for the molarity. Now, when it asks for molarity, I know that is number of moles divided by the number of liters. And I know if it says what is the molarity, I've got to have a number that goes here and a number that goes here, and then I'm going to divide them out. And the easiest number in the world to divide by is 1 liter, 1. So I'm going to assume the volume is equal to 1 liter, exactly. Now, my task now then becomes how many moles of the solute would be in that liter? So I need a liter. Look at the density. I can take the density is 1.67 grams of the solution. That's what the density is. It's on the solution. Per 1 milliliter. Now, if I've got a liter, then I want to change that to 1,000 milliliters would be 1 liter. So my milli would cancel. So the mass of the solution is going to be 1.67 times 1,000. And that'll be grams of solution. Now, I guess I need to spell that. I got to distinguish between solution, SOLUTION, grams of solution. And now I want to convert from grams of the solution to grams of solute. Okay? And I can do that because the percentage is given. If I had 100 grams of the solution, it would contain 75.5 grams of the solute. So at this stage now, I've got 1.67 times 1,000 times 75.50 or 5 divided by 100. And now I've got grams of the solution. Now I want to convert from grams of solution to moles of the solid. Grams of solute it is. That was U and that was a U. To moles of solute. Well, I know the formula now. Formula weight as the 1 mole of the compound would have a mass, I'll just put all the numbers here, 1.008. That's the hydrogen. Plus chlorine is 35.45 plus 4 times 16. So here's what I'm going to put in my calculator. 1.67 times 1,000 times 75.5 divided by 100 times 1.008 plus 35.45 plus 4 times 16. There is what I have to put in my calculator to get the answer. So it's 1.67 times 1,000. Yeah, I know I could divide that by 100 down here. Okay, I'm going to do what I set out to do. Times 75.5 divided by 100 and divided by the left parenthesis 1.008 plus 35.45 plus 4 times 16 and close my parenthesis and double check it. So I'm looking at my screen. 1.67 times 1,000 times 75 point that divided by 100 divided by a quantity 1.008 plus 35.45 plus 4 times 16. Looks like it's correct. So I'm coming out, my screen is saying 12.551010.635, and I've not rounded off anything. Okay? But I've got 3 significant figures, so it should round right there, which is 12.6 molar. Moles per 1 liter is molarity. So there's my answer. And that's response C on the exam. Now, you know, I'm not telling you any secrets. You know that that type of problem is going to be on the test. But I will always ask that question on this exam in some form, because that's a really important type of calculation to be able to do. And I've mentioned that before. You go get a bottle of some solution you bought from Dow Chemical or somebody, and on the label, it's going to give you exactly that information. It's going to tell you what's in the bottle, and they will actually give you the formula on the label. And it's going to give you the molecular weight of the compound on the label. It's going to give you the density of that solution in the bottle, and it won't give you the molarity. You'll have to determine that. And it'll give you things about purity, and it'll give you the percent composition, and it'll give you any appreciable impurities that might be in that bottle. It's all on that label. And so you need to be able to take that label and do that calculation. That's important. But remember where you're going, and then every step makes sense. Where you're going is, I want molarity. I need number of moles over number of liters. I need 2 numbers that I divide out. So I'm going to make this denominator a 1. I do that every single time. And then I'm calculating the number of moles in 1 liter. That will be molarity. When I got to here, that was moles. but it was the number of moles that I assumed way back up in the beginning when I said I'm going to do a liter. I multiplied the density by 1,000 because I wanted to go from milliliters to liters. And this was moles here, but it was moles for 1 liter, which gave me the molarity. Okay, good problem. All right, let's look at number 4. Okay. Okay, it's a nice stoichiometry problem. And now we've got the full gamut of problems. We've got stoichiometry essentially in all of its possible formats. Now, this one, you can look at it, and now I'm going to go over and set it up. I'll still be able to see what's going on over here. Okay, now, problem says what mass of chromium 3 oxide, so it's Cr2O3, and there's 10 of them in the balanced equation. Let's put my arrow down here a little better. Okay, now we'll form from 1.5 grams of propane. The equation is showing 3 propane, C3C3H8, and 35 milliliters of the chromic acid. The chromic acid formula, there's 20 of them, and it's H2Cr O4. I'm giving you the balanced equation, so you got your formulas here. You don't really need the names on this problem. Now, let's see. We wanted to know how many grams, what mass. Okay, the equation is showing 10 moles of that, and the formula mass of that is 152. Okay, so there is the problem amount is how many grams. The equation amount is 10 times that many grams. Now, we're reacting 1.5, I'm going to add another digit, 1.50 grams of the propane. The equation is showing 3 moles, and the molar mass of propane is 44.09. And I'm reacting it with 35 milliliters, so I'm going to write 35 times 10 to negative 3, and 35.0, and that's the volume, and in liters, and the molarity is 6.26. So if I take volume in liters and molarity in moles per liter, the product is going to be moles, so this is going to be moles. The equation is showing 20 moles. Okay, so it took a little time to do the setup, but it does give us a nice way of doing the problem. Because now if I imagine dividing what's here by what's here and dividing what's here by what's here, I can get my 2 rebalancing factors. All right, for the first one, it's going to be 1.5 divided by 3 and divided by 44.09. So it's 1.5 divided by 3 and divided by 44.09. So what I get for this one is 0.0113. And there's other digits. The next digit is a 4, and there's some more on my screen, but that should be enough to see which one is limiting. Now, this is 35 exponent negative 3, 35 second exponent negative 3. I want to multiply that by 6.26 and divide that by 20. And I'm coming out with pretty close, 0.010955. Okay, so comparing these two, 0.011 and 0.0109, this one is smaller by a little bit, but it'll be enough to make a difference if we use the wrong answer. And my guess is that one's on here somewhere. I use this rebalancing factor. Okay, now my answer is going to be this rebalancing factor multiplied by 10 and multiplied by 152. And it'll be in grams of the chromium-3 oxide. It turns out that I've still got that number on my screen, so all I've got to do is just say times 10 times 152. And I come out with the answer is 16.6516. That'll be grams of my chromium-3 oxide, Cr2O3. And the 3 significant figure round off would be 16.7. And that is my final answer. And it's response C on the exam. Feel free to ask questions anytime you have them along this problem, okay? Okay, all right. Let's go back and look at the next one. It's involving the same reaction. How many moles of products would form from 25 grams of 2.5 grams of propane and 75 milliliters of different molarity? So, okay. I'm doing propane again, so it's 3C3H8. I'm reacting it with the chromic acid, which is 20 times H2Cr04. Now I'm going to go to products, and it's asking for moles. So I'm just going to say it's 9 plus 10 plus 32. That's the moles of CO2 is 9. The moles of chromium-3 oxide is 10. And the moles of water is 32. So this is moles here of product. Now let's get our rebalancing factor. We got 2.5 grams. Again, there's 3 and 44.09 grams shown in the balanced equation. We've got 75 times 10 to the minus 3. That's milliliters. We multiply that by the molarity is 5.33. That'll be moles. The equation is showing 20 moles. Okay, now let's see which is the limiting reagent rebalancing factor. 2.5 divided by 3 and divided by 44.09. So for this one, I'm getting 0.0189 and some more digits. For this one, 75 with an exponent of -3 times 5.33 divided by 20. I get 0.01998 and some more digits. So it turns out that this one is the limiting reagent in this case. So like I told you before, since my calculator, I can't go back up there and get that number I still see up there on the screen. I'm just going to put it back in. It's not a big deal. I'm going to take 2.5 divided by 3 and divided by 44.09. be a big deal if I don't put the right answer in. 2.5 divided by 3 and divided by 44.09. And sure enough, I did get 0.018900733 showing up on my screen. So I need to multiply that by what's under my question mark. It was how many moles of this. So I'm going to multiply it by, I'm going to put it in just like that, times 9 plus 10 plus 32. And I get my answer is 0.9639374008 moles of product. And again, if I round off to 3, I get, we got a mic open somewhere. Okay, moles. And that's going to be D. Okay, and that's what we got. Okay, all righty. But I know why the mic was on. I didn't show you my paper, did I? Well, here was the setup. 2.5 grams of the propane, 75 milliliters of 5.33 molar. Divide the 2.5 by 3 and 44.09. I get this rebalancing factor. 75 times 10 minus 3 times 5.33 divided by 20. I got this one. So this is larger. This is the limiting reagent. So I take that number then and multiply it by the number of moles of product, and I get this answer, and it rounded off to 3 significant figures as 0.964 was response D. Okay. I wish I could get my laptop up. Okay. Is that going to be the right? No, that's not the right screen. Okay. Why am I not seeing it? Okay. Oh, there it is. Okay, now we're back to seeing the exam. And let's go on to number 6. Several reactions involving the same reaction. And again, I like to do that. I need to test on lots of different types of stoichiometry. So I like to use a reaction that I can do for all of them. And so I'm using the same equation all the way down, and I like to do that. Okay, this one now is, we're taking the yield into account. I want to form 1.5 grams of the chromium-3 oxide from the chromic acid, and it's 6.25 molar now. So I want to know how much of that acid would I use if the reaction is only 68.6%. So the way we're going to always handle percent yield is in the very last part of the calculation. So let's say I wanted to make my chromium-3 oxide is 10 Cr2O3. I'm going to make that from 20 H2Cr O4. And I don't care about the other things. That's the only things that are involved in this reaction. If I take the volume in liters times the molarity in moles, that's going to be molarity, moles per liter. That's going to be moles, and this will be 20 moles down here. Now the amount of the chromium 3 oxide I want is 1.5 grams. The equation is showing 10 moles, and the molar mass is 152. So this is going to define my rebalancing factor. And that's going to be 1.50 divided by 10 and divided by 152. And my answer in moles is going to be the rebalancing factor, 1.5 divided by 10 divided by 152 and multiplied by 20. And now I'll get moles of the H2CrO4, chromic acid. Okay, now, so I can do that math. 1.5 divided by 10 divided by 152 and multiplied by 20. So that should give me my answer is 0.0197368421 moles of that. Now, that has to be equal to the volume in liters times the molarity. The molarity given in the problem was 6.25. So the volume is going to be this number divided by 6.25. Okay, now that number is still on my screen, so I just need to divide by 6.25. And I come up with the volume is going to be 0.003157 and some other digits. That's in liters. I look at my answer is in, oh yeah. I started to panic. I thought, that's not going to give one of those answers, but I'm not done yet. Okay, well, one liter, well, I want milliliters. So to be consistent, this would be 10 to the minus 3 liters. I've got milli and milli here, and that liters would cancel. So I want to divide that by 1 times 10 negative 3. That, of course, is the same thing as multiplying by 1,000. So I'm coming up with 3.15789, a whole bunch of digits like that, milliliters. And 3.15 is one of the answers, but it's the wrong answer. Oops, what did we do wrong? Well, we haven't done anything wrong. It's the percent yield problem. Now, this is how much that I would want to make for 100% yield. Now, but I'm going to have to start more than that because I'm going to try to make enough of this so when I multiply that by 0.7, where is the problem? 0.686, I come up with 1.5 grams. So I got to scale up. So what I'm going to do is take this number and divide it by the decimal equivalent is 0.686, 68.6%. So when I do that, take that number and divide it by 0.686, I come up with what's listed as the right answer. The volume needed if 68.6%, that's going to be equal to 4.60 3 digits, and of course rounding off to 3 significant figures, 4.60 milliliters is my final answer, and that is A on the exam. Now, there are logically two ways you can handle a percent yield. They can be of the form, how much of this chromium 3 oxide would you get if you reacted 4.6 milliliters of 6.5 molar chromic acid if the yield were only 68.6%. If you're dealing with that, you're going to get an answer, and then you're going to multiply by that fraction, 0.686, because the theoretical amount is going to be reduced, and so you want to multiply by a number less than 1, 0.686. If you're doing the problem like we're doing here, and you want to know, well, how much starting material do I need to take in order to get 1.5 grams over here, then I'm going to work it as if I were working it without taking into account the percent yield. And then I'm going to scale it up. The way you scale up is you divide by that number less than 1. That's going to make it bigger. So I'm either going to multiply by the fraction if that is what I'm doing for the product. I'm going to divide by the fraction if that's what if the percent yield is based on the reactant. So depending on the wording of the problem, if you're calculating a reactant, you're going to have to scale up. If you're calculating a product, you're going to have to scale down. And so you have to read the wording of the problem to see which way to go. And I'm guessing, yeah, I'm thinking probably the 2.16 answer. Let's go back to screen share. I'm guessing this answer here is probably 0.686 times that one. That's what I'm kind of guessing. And this one looks like, I don't know why I got that one. I don't see it. There's a reason somewhere you can get that number. Okay. Let me out of paper. Right. And moving right along, we're all the way up to number 7 now. Okay. All right. What volume of CO2 gas would form at 25 degrees and 735 torr by reacting 1.5 grams of propane? Okay, here we go. We got propane, and this is number 7. It's C3H8, and the equation has 3 of them. And we are asked about oxygen, carbon dioxide, and the CO2. We've got 9 of them. And we want to make, we're going to use 1.5 grams of propane. Now, we want a volume, and the volume is going to be nRT divided by P using the ideal gas equation. So I need to know the number of moles. So the first thing I'm going to calculate here is how many moles. Now let's do the setup. This is in moles, the equation showing 9. This is in grams, the equation is showing 3 times 44.09.
Dr. Pearson, can you switch your camera back?
Oh, yes, thank you. Thank you, thank you, thank you. There you go. Now, okay, so here's setup. I had 3 propanes to go to 9 CO2s. The problem wanted to know what volume of the CO2 at some temperature and pressure. So I'm going to get that from the ideal gas equation. D is nRT over P, which means I need to know the number of moles. So I'm going to solve my problem first in moles. The equation is showing 9 moles. This is in grams, the equation is showing that much. So my answer is going to be equal to the rebalancing factor, 1.50, divide by 3, and divide by 44.09, multiplied by what I'm doing over here, 9 moles. Okay, so that's give me the mass. That'll give me my answer in moles. 1.5 divide by 3 and divide by 44.09 and multiply by 9. 0.5 divided by 3 divided by 4 multiply by 9. Yep, that looks like what I entered. So what I'm coming out with now is my number of moles is going to be equal to 0.10206 and a whole bunch of other digits. Now what I'm going to do is say, okay, volume is going to be equal to my N. That's going to be that number right there. R is 0.0821. Temperature is 25 degrees, so that's going to be 298.15 degrees Kelvin. nRT divided by the P, and the pressure is 735 divided by 760. We got to get to atmospheres. 1 atmosphere is 760 torr. So 735 divided by 760 is my pressure in atmospheres, which is what I have to have for this problem. So now I'm going to do the math, and the way I'm going to, I could do it just like this with a parenthesis around it, but I'm just going to take the denominator of the denominator and put it in the numerator. That's what you do. Okay, so I've got this number for the number of moles on my screen right now. So I'm going to multiply that times 0.0821 times my temperature is 298.15. Don't forget to convert from Celsius to kelvins. And then I want to multiply that by the 760 that I'm going to move upstairs and divide it by 735. So 0.0821, 298.15 times 760 divided by 735. It looks like this is coming out. The volume is going to be, my calculator is saying 2.5833310677, and that's going to be, volume is going to be, I get 2.58. The problem answer is 2.57, but that is okay. That's plus or minus 1. And that is response B on the test. Probably I did the 298.15 on my calculator. I'm guessing when I did this for the key, I just did 298, but that's okay. We don't panic unless we don't agree with the exam to plus or minus 1 in the last digit on the right. If we don't agree at that level, then somebody made a mistake. Either I made a mistake in keying or you made a mistake in doing the calculation. I always try to make sure that that's true so that you don't just make a mistake and get an answer that's close to mine and think, oh, well, that's the answer. That's probably not going to be correct. So you always test yourself to see you get plus or minus 1 in that last significant digit. Okay, and now I need to share screen again. Oopsie daisy. We're ready for number 7, I think. No, we did number 7. That was number 7. We need ready for number 8. Again, using the same equation. And it says what volume of propane as a gas at some temperature and pressure would react with 35 milliliters of the chromic acid. So this one now we've got gas and volume and molarity types of stoichiometry. So this test has virtually all of the possible types of stoichiometry you would ever need to do. So it's 3C3H8, and we're reacting that with 20 H2CrO4s. And now we're reacting 75 times 10 to the negative 3 liters. The molarity of the solution in this case is 3.25. And that'll be moles. The equation is showing 20 moles. Now we want to know what volume of this. So again, we're going to first find out number of moles.
Hey, Dr. Pearson?
Yes.
Screen.
You need to see my paper again. Thank you. I'm sorry. Here's the setup again. We're doing 3 propanes and 20 chromic acids. The problem showed 75 times 10 negative 3 liters at 3.25 molar. Multiply that, you get moles. Equation showing 20 moles. Over here, we asked for a volume at some temperature and pressure of a gas. So we're going to use the ideal gas equation again and solve first in moles. So the equation is showing 3 moles. So my answer now in moles is going to be the rebalancing factor is 75 times 10 negative third times 3.25 divided by 20. And then multiplied by 3. That's the rebalancing factor times what's under my question mark. Okay, so now I just need to do the math. It's 75 with an exponent that's negative 3, multiplied by 3.25, divide by 20, and divide by 3. No, go back up. I need to multiply by 3. Yeah, there we go. 75 exponent negative 3 times 3.25 divided by 20 times 3. Okay, that happens. So I'm coming out with the number of moles is going to be equal to 0.0365625. That's all the digits. And V is equal to nRT divided by P for a gas. And there is my value to go in for N. And pressure and temperature. The temperature that I'm putting in here is 25 plus 273. I'll put the other 0.15 on, but I don't know whether it matters. The pressure now we've got is 735 divided by 760. So we're going to do the same trick later. We're going to put all of this stuff in, but I'm going to put the 760 upstairs because it's in the denominator of the denominator. And it goes to the numerator. Maybe I'll do that right here. I'll just put it up here, 760. Now I got it. Now I've got everything on my screen. So I've got my answer. So I'm going to take that and multiply it by R times 0.0821 times 298.15 times 760 divided by 735. Okay, so what I'm coming out with is 0. Volume in this point is 0.925 4 and a whole bunch of other digits. But this digit is less than 5, so it's 0.925. What's the volume unit? That's right, it's liters. I'm looking at my answers, they're all in milliliters. So I need to convert from liters to milliliters. Milli is 10 to the negative 3, 10 to the minus 3. So I want to divide my answer, divide it by 1 second exponent negative 3. And I get 925.4. So that comes out to be 925 rounded to 3 sig figs milliliters. And that's response D on the exam. Okay, so, all right, we're good. And now let's go back and look at the next one. Are we doing good? Okay.
Yes.
Okay. Good. All right. Okay. Now we've got a latex balloon is inflated to a volume of 5 liters. What mass of helium is required to fill the balloon at 25 degrees in 1 atmosphere? Okay, that's just a straightforward ideal gas equation. So number 9. We're going to do PV equals nRT. We know the temperature is 298.15. We know the volume is 5 liters. To be sure to check that it's in liters because that's what we're going to do with R. If that had not been in liters, we'd need to change it to liters. And the pressure is going to be 1 atmosphere. So I can solve this for N. So let's do. So N is equal to P times V over R and T. So the pressure is 1 atmosphere. The volume is 5 liters. R is 0.0821. And the temperature is 298.15, maybe. Okay, so I can solve for the number of moles. So I've got 5 divided by 0.0821 and divided by, okay, I don't see screen share, so you are watching my paper. Okay, good. And divided by 298.15. 5 divided by 0.821. Yes. Okay, so what I'm coming out with is the number of moles is 0.204, 26, and a bunch of other digits. Moles. And now it's helium. But the answer is in grams, so I have to convert this from moles to grams. Moles of helium to grams of helium. 1 mole of helium, it's 4. 4 is probably close enough. Let's see. 4.0026. I'd say that 4 would have been close enough. Yes.
Why did you put the pressure and the volume on the? Why did you put the 1 atmosphere on the top and the why didn't you put it underneath?
Okay, I'm solving for N. The
Uh-huh.
way I'm going to get N by itself is divide both sides through by RT.
Oh, okay. Sorry, I was reading that wrong.
Okay, so the number of moles is going to be P times V over R and T.
Okay.
And that's what we did here. P times V over R and T. And now there's 4.00 grams of helium in 1 mole of helium. So I just need to multiply my answer on my screen by 4. And I get 0.817056 and bunches of digits, and 0.817 is what I'm getting. The answer shown on the exam is 0.818. So that's again plus or minus 1 in that last digit. So the response is C on the test. Okay, we need to do a screen share so you can see the next question. That would be number 10. Calculate the number of dichlorine molecules in a 5 milliliter container at 40 degrees C and a pressure of 2.14 pascals. And I gave you the conversion factor that 101.3 kilopascals is 760 torr or 1 atmosphere. It's the same thing. Okay, so let's go back and get it. Now it's an ideal gas equation, and we got Cl2 is the compound that's in there, and we've got volume is going to be 5 milliliters, and we're asked to calculate how many molecules. Now, it's an ideal gas problem, so the first thing I'm still going to do is I'm going to solve for the number of moles. Number of moles is going to be, again, P times V divided by R and T. So the number of moles is going to be the pressure. The pressure is, maybe I'll do a sidebar over here. Pressure is 2.14 times 10 to the 4th pascals. And 101.3 times 10 to the 3rd kilopascals. Pull this over a little bit. You can't read it. I can't either. 2.14 times 10 to the 4th pascals. And I want my conversion factor to be 101.3. Kilo is 10 to the 3rd pascals. Now my units will cancel. And that's 1 atmosphere. It's 760 torr, but we need pressure in atmospheres. So this is going to be my pressure calculation. So I can go ahead and do that right now. 2.14 with an exponent of 4. I want to divide it by 101.3 with an exponent. That's 3. And that gives me 0.21125 and a bunch of digits. Atmospheres is going to be my pressure. Now, I'm going to now plug that in. My number of moles is going to be P times V over R and T. So let's put my numbers in. Pressure I just calculated. It's going to be that number right there. Volume, it was 5 milliliters, right? So it's 5.00 times 10 minus 3. And now that's going to be in liters. That's good. and I want R 0.0821. And what do we have for temperature? 40 degrees Celsius. So that's 40 plus 273.15. Okay, so I got everything ready to enter it in my calculator. The answer from the previous problem is going here, so I'm just going to say times 5 with an exponent of -3, divide by 0.0821, and divide by a left parenthesis 40 plus 273.15, close the parenthesis. And now I'm double checking. I've got my answer, times 5 times 10 -3rd, divided by 0.0821, divided by a left parenthesis 40 plus 273.15, close the parenthesis. That's what it says on my screen. So my answer for the number of moles is equal to 4.108 and some more digits times 10 minus 5th moles. Now, we wanted to go from moles to molecules. Well, 1 mole of anything is 6.02 times 10 to the 23rd of those things. So this is now going to be molecules. Okay, so I need to multiply by Avogadro's number times 6.02 with an exponent that's 23. And I'm getting 2.47329, digits like that, times 10 to the 19th molecules. And if I round it off to one significant figure, two significant figures, one decimal place, like the answers, that would be 2.5 times 10 to the 19th. I've got, and response A is 2.6 times 10 to the 19th. So again, we're plus or minus 1. So A is the correct answer then. Okay, I need to do screen share. Get to the next one. All right, now we're going mixture of 5 moles of nitrogen gas and 8 moles of oxygen gas. The total pressure is 760 torr. What would be the pressure of nitrogen in the mixture? Well, that's just a straight plug-in for Rayleigh's law. Number 11, let's go back here. All right, so we've got pressure of some component in a mixture is going to be the mole fraction of that component times the total pressure. And that's the statement of Rayleigh's law. And so if I want the pressure, what's the pressure of nitrogen? That's going to be the mole fraction of the nitrogen times the total pressure. Total pressure 760 torr. So I need to get the mole fraction of the nitrogen. Mole fraction of nitrogen is going to be the moles of nitrogen. If we have 5 of them. And we have total moles is in the container is 5 moles of nitrogen and 8 moles of oxygen. So the mole fraction is 5 divided by 13, I guess. So the pressure of the nitrogen, I'll save space, pressure of the N2 is going to be equal to 5 divided by 13 times 760. So that should be the answer. So 5 divided by 13 and multiplied by 760. That's a pretty straightforward one. And what we're coming out with for the answer, we got 292.307 and a whole bunch of digits. I need 3 significant figures, so the answer is just going to be 292. And of course, the unit is torr. And that's response A on the quiz, so we're good. And the next one is number 12. Okay, number 12 is a Graham's Law problem. So let's set up. Now we've got an experiment. We've got O2 gas. And it's found in the experiment, it takes the O2 gas. So I'm going to say the velocity of the, maybe I use a little more case V, so it's not, doesn't look like volume. So the O2, the velocity of the O2 gas is going to be 35 centimeters. I got to get where I can see my screen a little better. 35 centimeters in 5 seconds. Well, I can see an answer right there. It's, divide that out, that's a 7. So it's 7 centimeters per second. And the other gas that I've got is SO2. And if I want the velocity of the SO2 gas, then I can do these by Graham's law, because it says the velocity of the SO2 divided by the velocity of O2 would be the square root molecular weight of O2 divided by molecular weight of the SO2. Remember, it's an inverse relationship. The velocity of a gas is inversely proportional to the square root of its molecular weight. So this is what we get for the two gases. Now, so I can solve for the velocity of SO2. Velocity of SO2 would be equal to, multiply through by velocity of O2, it's velocity of O2 times the square root of, molecular weight of O2 is 2 times 16, 32. Molecular weight of SO2 is 32 plus 2 times 16. And so I know that number, that's 7 centimeters per second times the square root of that quantity. So let's just go ahead and do the square root right now. So I'm going to take 2 times 16. I'm going to divide it by left 32 plus 2 times 16 right. And if I do that, this reduces to 0.5. Now I want to take the square root, second answer, and I get 0.707. So the velocity of the SO2 is 7 times 0.707, and this is going to be in now centimeters per second. So you can see it. Okay, so I'm going to need to multiply by 7. So I'm coming out with 4.9. Velocity of the SO2 is 4.9497. 4.9497, and of course still centimeters per second. Now at this stage, it would be kind of wise to do a reality check. Does this make sense? The velocity of oxygen is 7 centimeters per second, and the velocity of SO2 is less than that. Does that make sense? Does, doesn't it? The heavier gas should travel slower. And so this number must be less than 7. If you put this factor in wrong, then you'll get a number greater than 7. That would tell you you've messed up. Okay. Now, got a little white space right over here, so let me see if I can use that. I want, how long does it take for SO2 to diffuse 35 centimeters? So I've got 35 centimeters. Now for the SO2, it's going to be traveling at 4.94 and digits centimeters in 1 second. So I need to divide that out, and I get 35 divided by the answer I've got on my screen, and I get 7.071 seconds. And now again, it would be time for a reality check. Should it take SO2 more time or less time than it took oxygen to do the same thing? And that's right. It should take longer, shouldn't it? SO2 is heavier. It's going to take longer to go 35 centimeters than the oxygen. So the numbers make sense, and it's response D on the test. So it worked out okay. All right, let's look at the screen. And we're ready for number 13. Oh me, we knew this one's coming, didn't we? We got one of those terrible old van der Waals equations problems to deal with, but hey, it's not a big deal. Let's show you that it's not. Okay, 13. Now, it's a van der Waals problem, so I've got to know the van der Waals equation, and I'm not going to give it to you on this test. Now, on the final exam, I probably would, but not here, because this was a point of important discussion here, and I want you to know what the van der Waals equation is, at least for now. So P plus A n squared divided by V squared. We had to make a pressure correction, remember? And it was additive. We had to make a volume correction to subtract off the volume of molecules. That was N times B. And then we set that equal to right-hand side. PV equals N RT. So the only thing we've changed is we've added this to the ideal gas pressure, and we've subtracted the moles of the volume of 1 mole of molecules. That's what B is. All right, so now let's see what the problem. Calculate the pressure. So I'm going to need to get the pressure by itself. So how can I do that? Well, I want to divide both sides by V minus NB. So I want N RT divided by quantity V minus NB. Now I want to get rid of this, so I want to subtract A n squared over v squared from both sides. So P is equal to n RT divided by the quantity V minus NB minus A n squared divided by V squared. Okay, there is what we're going to have to solve. And I see another one bites the dust. Let's go get a new one. Okay. Now we're ready to put the numbers in. Now okay, we're going to need n. N is going to be equal to, it's 24.5 grams of ammonia. Ammonia is NH3. Now, I guess I didn't give you that formula, so you need to know the difference between ammonium ion, and ammonia. And in ammonia is NH3, ammonium is NH4 plus. Okay, so I've got nitrogen, it's 14.01, 3 hydrogens, 3 times 1.008. So that's going to be my number of moles. R, of course, we know R is 0.0821 liter atmospheres per mole per Kelvin. What about the temperature? The temperature is what? 300 Celsius, so it's 300 plus 273.15. What else do we need? Volume. We need a volume. The volume is equal to 2.15, and it is liters, so that's good. Okay, we've got N, R, T, and V. We're solving for P. We need the A and the B constants. The A and the B constants, well, I'll go ahead and copy them back down here. The A value is 4.3044, and the B value is 0.03787. Okay, I got all my data in here. Now, here's the way I'm going to do. I put this one first because I want to put that one into my calculator. I'm going to need it here and here and here. So I want to do this on the calculator without doing any of these calculations and writing answers down. Now, so what I'm going to do is I'm going to say P is equal to. Now I want N, so let's do N. N is 24.5. I want to divide by left parenthesis 14.01 plus 3 times 1.008 close parenthesis. Now, when I do this equal, I'm going to get the value of N. Okay, now, I mean, I'll tell you, but I'm not writing it down to put it back in later. 1.438, 299, a whole bunch of digits. That's what I calculated for N. Now, but my problem says take N and multiply it by R. So I'm going to take that times 0.0821 R times T. The temperature is left parenthesis, 300 plus 273.15, close that parenthesis. Now I've got T. I want to divide it by, I need a left parenthesis. Divide by a left parenthesis, the volume. The volume is 2.15. 2.15 minus N. Well, the N is the answer I've got. So minus second answer. Now, times B. The B constant is 0.037847. And right there at the B, I need to close my parenthesis. Close my parenthesis. Now I need to subtract the A value. The A value is here, 4.3. So subtract 4.3044 times N squared. That's still in my answer. So times second answer squared. And now I want to divide by V squared. And there's my V, 2.15 squared. Now, I'm looking at my screen to double check and see if I read this off. Okay, are we good? Okay, all right, I'm looking at my screen to see my answer is N. So yes, I've got answer times 0.0821 times the temperature, left parenthesis, 300 plus 273.15. Then I close the parenthesis. I want to divide by a left parenthesis. Volume is 2.15, yes, minus the answer times the B constant, 0.037847. And then I'm closing my parenthesis. Yes. Then I'm subtracting A is 4.3044 times N. And that's answer. And now square it. Yes. And divide it by the volume is 2.15. And that's squared. Well, it looks like I've entered the data correctly in my calculator. So I put, oh my goodness. I've got an error in there somewhere. Let me go back and see where it is. Oh, I did not see it on the way through. Answer times 0.0821 times 300, 0.2, 300. Wait a minute. Yes, there it is right there. Now, since that's all in one line, I can get I can if I hadn't screwed it up. I need to exit out of this. So where can I get? Push the wrong button. Okay. Oh. Okay. Now, second entry. Now I'm going to go back up here and I see where the mistake is. It was 300 plus 300. That should have been a plus. Plus 273.15. I think that fixed it. Yes, I got something to work. So what I've come out with is 30.3704, whole bunch of digits. That should be in atmospheres. And I'm seeing the answer given in pascals. So I'm going to convert from atmospheres. 1 atmosphere is 101.3 times 10 to the third. Yes, you need to see the screen again, don't you?
No.
Oh,
Mind if I take a picture of your calculator?
I'm sorry?
Mind if I take a picture of your calculator?
I'll see what I can do is see if I can give you a screenshot that.
Thank
maybe
you. I got
can, can you get it?
Yes, sir.
Okay, very good. Okay, so I got 30.370778 atmospheres. I'm going to multiply that by 101.3 times 10 to the third pascals, 101.3 kilopascals. And so I'm going to multiply that by 101.3 with an exponent of 3. And I should get 3.08 times 10. And let's see, I'm going to have to count 1, 2, 3, 4, 5, 10 to the 6 pascals. Yeah, I'm off a little bit, but the answer is 3.19. So if I'm looking at the second significant figure, I'm okay, but I should be better than that. There's a chance there's still a slight mistake, and it could be way back up here when I did the temperature. I put it in as 273.15. That could be enough when you multiply by a million to make that much difference. So my guess is when I did the calculation for the key, I just put in probably 573 for the temperature. But I'm pretty sure we got it set up right. We double checked it. Everything looked good. And we're getting 3.1 instead of 3.2. So, okay, a little further off than I wanted to be, but I'm pretty sure that's correct. I don't think there's another mistake. Unfortunately, there's two answers there that I'll go back and double check these two answers on this key. Let's see. I need to screen share and show you what I'm talking about. It turns out that would have been a pretty tough answer. I don't usually put two answers that close together. But 3.19 times 10 to the 6 is what I should have gotten. And one of the foils is 3.01. So, you know, the answer I got is pretty hard to distinguish between those two. Okay.
I got the same one as you did when I did it.
You got what answer?
I got the same answer that you got, or about the same, 3.08.
Yeah.
3.76529.
Yeah. I think that's correct. I think it's just a matter of maybe I had the calculation off a little bit, and I'm thinking what I did is probably just put the temperature in as 573 instead of 573.15 like I did here. But I'm sure we worked it right. But I mean, I wanted to make the point that you can do all of this inside the calculator. And that's probably the best way to do it. Because there's so much rounding off stuff, if you copy intermediate numbers down, some of these numbers in the middle up here, if you copied them down, you'd have like 8 significant figures on your calculator. And don't forget, when you get to the final answer, we're multiplying by over 1 million and doing that conversion. So any round off that you got anywhere in there is going to really show up. So the best thing to do is to try to always do the calculations so that you don't have to round off anything to get to the answer. Okay, when certain process, you know what? Let's take a 5-minute break or something, and give ourselves a little rest for a moment, and maybe 10 o'clock to 5 after 10, we'll come back and finish this up. We're at the halfway point now. So let's stop the screen share and let's pause the recording. And now let's look at number 16.
Dr. Pearson, I don't
Yes.
think 14 or 15.
I'm sorry?
I don't think we did 14 or 15.
Oh, we didn't?
I don't think so.
You're right. We didn't. Oh, me. I thought we were further along than we are. Well, thank you. We'll pick up with number 14 then. And no, wait, ideal gas. We haven't done the ideal gas problem. That's why I probably thought I'd done it. Okay, number 14. We did van der Waals first. Okay, so number 14, we want a van der Waals gas and an ideal gas now, and the equation is going to be P times V equals nRT. And now we've got, we asked for what would be the pressure. So pressure is going to be nRT over V. That should be a little easier calculation than we did a moment ago. We've got 24.5 grams of ammonia. We got to convert that to moles. So 14.01 plus 3 times 1.008 molecular weight. So we can go ahead and get the N here. Let's do it. It's going to be 24.5. 24.5 divided by 14.01 plus 3 times 1.008. That's another place where the answers can be made different because, you know, maybe we didn't round off things the same as we did. But anyhow, I'm coming out with 1.438 299 bunch more digits moles. And now I can solve for P. It's N times R times T. Temperature, let's see what the temperature was. Temperature, oh, you know, it didn't give me one, but I'm sure it was intended to be the same as the one we used up here. So I'm going to say T is 300 degrees C, but I don't see it on this problem. So I'm sure if they, it was intended to show the difference between the van der Waals and the ideal gas in this particular example. Okay, all right. So N I've got on my screen. So I'm going to say times the R is 0.0821 times the temperature is going to be 300 plus 273.15. So that's nRT, and divided by the volume is 2.15 and is liters. That would be okay. So I'm coming out with 31.479 in digits atmospheres. I want to go from atmospheres to pascals, the same answer as units. So 1 atmosphere is 101.3 kilo, is 10 to the third pascals. And that's our unit in there. Okay, so I've got this number. I'll multiply it by 101.3 times 101.3 exponent third. And I come up with pressure is going to be 3.188833 more digits, and I've got 1, 2, 3, 4, 6 times 10 to the 6. I round off to 3 significant figures is 3.19 is equal to that answer. Now I understand the mystery of why I had 3.19 as one of the foils in the other problem. And that's because now didn't I get 3 point? Where's my answer? Yeah, the reason why we got screwed up a while ago was I was looking at the answers on 14 instead of the answers on 13. The answer on 13 was 3.08 times 10 to the 6th. So we did get it right on that van der Waals equation. I couldn't believe that I hadn't caught any mistakes long before this on this test. Okay, but anyhow, the answer is 3.19 times 10 to the 6th pascals. And that's what we would get if we had an ideal gas equation, ideal gas. Now you can see in these two cases, it's not very different. And the reason why it's not very different is we're way up at 300 degrees Celsius. Ammonia boils way down, I don't know, I'd guess somewhere about minus 50 or 60. So we're far above the boiling point. So this gas ought to behave pretty much ideal. And when we got the pressures, we got 31 atmospheres. Now that's a little high pressure in order to be at ideal behavior, but it's not that far out of the range. If we're talking about 150 atmospheres, yes, that's definitely going to be non-ideal, and there'll be a big difference between the ideal pressure and the van der Waals pressure if you're at a really, really high pressure. But the thing that's making this gas behave more like an ideal gas is that we are so far above its boiling point that it's going to behave very much like an ideal gas. So I'm guessing that's the point of another question a little later on. Okay, so let's turn on screen share again so we can see the next problem. Okay, so we got number 14, right? Now let's do number 15. All right, so number 15, we got a process is carried out in a sealed rigid container. Now, what did that tell me? Well, anything that's in a sealed rigid container, delta V is going to be 0.
Dr. Pierce, could you switch your screen?
Yes.
Thank you.
Yeah. So anything that's carried out in a sealed rigid container, the volume is not going to change. So when I measure a heat flow, Q, that's going to be equal to Q when the volume is constant. And that's going to tell us that that's also going to be delta E. So there may be some other, that may not be the point of this problem. I don't know. Let's just look and see what we got. But it's in a sealed rigid container. Then it says the heat flow, Q at constant volume, is going to be equal to, the problem says 50.6 joules. Okay, so we got that much information. When the process is carried out at constant pressure. Now, we are given Q at constant pressure. Q at constant pressure, we're told, is minus. Oh, this was a minus up here. That would have been, yeah, I didn't see my minus sign. I'm going to just cross that out so I know I got it, what I'm looking at. Minus 50.6 joules. And Q at constant pressure is minus 72.2 joules. And now that's going to be equal to also delta H. And this one up here is also equal to delta E. So this is all of the information that I see I can get right now from the data that's given in the problem. Well, this one's kind of meant to be a curve raiser because it asks for what is Q at constant pressure. Well, I just have to read the problem, minus 72.2. And that's going to be D on that test. Okay. Now, number 16, maybe we're going to do something a little more interesting. I don't know. Let's see. Well, process carried out, sealed, same data. Q at constant volume is minus 50.6. Q at constant pressure is minus 72. And we're getting to work. Now, the easiest way to get to that from here is delta H is equal to delta E plus P delta V and minus P delta V is equal to work. So P delta V is equal minus work. So delta H, I've got a number for it. It's right there. It's minus 72.2 is equal to delta E. I've got a number. It's minus 50.6 minus W. So if I rearrange this and solve for W, W would be equal to 50 minus 50.6. Moving this across would make it plus 72.2. Of course, the unit is joules. So the work is going to be equal to 72.2 minus 50.6. So this is 72.2 minus 50.6. I get plus 21.6 joules. And that's response A on the test. Now ready for number 17. Same set of data, but we want to know what delta E is. Well, since we've already got stuff here, I'm just going to go on the bottom of my sheet right here and we can write the answers down, because for number 17, we've got the same data, but we want to know what's the delta E. Well, we did that way back up here in the beginning. Delta E was minus Q at constant volume, so that's going to be equal to minus 50.6 joules. And on the question, that's response A. So go back and look and go on. Okay, so we're good there. Okay, number 18. And it's the same data, and we want delta H. Well, we've already done that way back up here too. If we go right in the beginning, we said Q at constant pressure was given at minus 72. So that's going to be the delta H is minus 72.2 joules. So minus 72.2, that's the Q at constant pressure, which we calculated earlier. And that answer is response B on the test, and so we're good to go. Okay, now those are kind of trivial questions, but they really are kind of important concepts. And so there's like 3 or 4 questions there that I'm really expecting everybody to get. Okay, when reaction is considered for thermodynamic studies, what is the partial pressure of the gas in the standard mixture? Well, I don't need to go over there, because remember what I said. I'm going to give you details about this one. In this reaction, propane and oxygen is CO2 and water vapor. Notice everything is gaseous, so what I'm saying is going to be true. The standard state for each gas is 1 atmosphere pressure. So if I want to know what the partial pressure of any of the gases in this mixture is, it's 1 atmosphere pressure. If I want to know what the total pressure is, you've got to remember everything in, if I go to the lab, am I going to take propane and oxygen and mix it with carbon dioxide and water vapor to study this reaction? No, of course not. But remember, the starting point is this, the ending point is this. It doesn't matter how we get from this side to this side. So we are going to take the hypothetical case that we've got a mixture containing all 4 of these gases. If that had another reactant, there would be 3 on this side, 2 on that, would be 5. It's the number of gases. Each one of the gases exerts a pressure of 1 atmosphere pressure. So the total pressure in the container is 1, 2, 3, 4, the sum of the partial pressures. Now, what if this one had been liquid water? Liquid water, water's liquid at 25 degrees. So if we're talking about a reality check, if we're at 25 degrees, which is where all our data is taken, the water ought to be a liquid. Well, it's shown as a gas here. What if I made it a liquid? How would that change the standard state? Well, it would just say, I've got 1 atmosphere pressure of this gas and 1 atmosphere pressure of this gas and 1 atmosphere pressure of this gas. I've got 3 atmospheres pressure in the container. I don't count the water if it's a liquid. Now, it will turn out, and we'll get to that in Gen Chem 2, we do a funny standard state when we're talking about liquids. We define our standard state as 1 mole per liter. Well, can you have liquid water at 1 mole per liter? No, you cannot. The density of water is 1 gram per milliliter, 1,000 grams per liter. That's 55.5 moles per liter. In reality, the water would be at 55.5 molar. Our standard state is 1 molar. Now, can we create that state? No. What difference does it make? It's a part of the definition of the standard. And so remember, when we're dealing with this, we're talking about standard states. It's a hypothetical reaction that we're not really doing. But we can calculate for that what would really happen in the one we are doing. Okay? So this is an important concept. Please carry that with you to Gen Chem 2, that you understand that if you've got gases inside a container, the standard state is 1 atmosphere pressure of that gas, not 1 atmosphere pressure in the lab. 1 atmosphere pressure for that gas. The pressure on this container is, in this case, 4 atmospheres. All right, so there would be another way to ask that same question. Let's look at number 20. And now we're going to use a data page here. Again, if I give you a problem like this, well, what do you mean if? When I give you a problem like this, I will give you the data you need for the heats of formation. Probably not in a data table because I've not been able to get that to code right yet. Maybe I'll learn someday, but I can't make it work. And I have tried. Somehow or other, when I try to put a table in there, it tries to put a link instead. And I just can't get it to work right. Okay, enough of that. All right, we got a reaction. The reaction is, and we want to calculate the heat of a reaction. We've got 2C3H8 and 7 O2s. And that will burn to make 6 CO2s and 8 H2Os. And it is gaseous, everything. and the state is important. I want to calculate the delta H of the reaction. We put a little superscript up there meaning the standard state value. What that means is what we just talked about a while ago. It means in a setup that has 1 mole of each gas present. I'm sorry, 1 atmosphere pressure of each gas present. And temperature is 298 or 25 degrees Celsius for us. So that's what it means. That's going to be equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Okay, so let's put the numbers in. So the delta H for my reaction is going to be equal to 6 times the delta H of formation of CO2, and it is gaseous, plus 8 times the delta H of formation of H2O, and it is gaseous. Now I need to subtract off the sum of the heats of formation of the reactants. That's going to be 2 times the delta H for formation of C3H8. Now, it would be minus 7 times the heat of formation of O2 gaseous, but O2 gaseous is the reference state for oxygen, and everything in its standard state is 0. So 7 times 0, I'm not going to include it, but I've got my numbers now. So let's see, I need to go back over here so you can go with me to the somewhere. Where was it? Was it at the beginning? Yeah, here we go. Here heats of formation. So I want 6 times the heat of formation of CO2. So I'm looking at the CO2. Gaseous CO2 is right there. It's minus 393. I'll show you my paper again when I get the data copied down. Minus 393.5 plus 8 times the delta H of formation of gaseous water. Now you see that's what we need to worry about. There's a difference between gaseous water and liquid water. And the liquid water is minus 285.8. Gaseous water is minus 241.8. So the number we want for this problem is minus 241.8. And minus twice the propane value. Propane is right there. It's minus 103.8. Okay, so now we can go, well, let's go back to the problem. We're looking at number 20. So I'm going to put it back down here on number 20. And then let's go over here to the pad and do the math. So here's the calculation that we need to do to get this reaction. And you know, I'm going to do it exactly the way you see it right there. I'm going to put it on my calculator. I'm going to say 6 times minus 393.5 plus 8 times minus 241.8 minus a minus 103.8. Now, I'm looking at my screen. It's saying 6 times 393.5 plus 8 times a minus 241.8 minus the minus 103.8. So when I do that calculation, I'm coming out with minus 4196.6. Ooh. I am saying,
Dr. Pearson,
yes,
Dr. Should you have multiplied the minus 103.8 times 2?
thank you, thank you, thank you. Yes, I should have. Thank you for catching that. So it would be minus, I should have a 2 right there. That's why I'm coming out with a bad number. All right, back up in point. I'll just redo it. 6 times minus 3, 93.5, plus 8 times minus 241.8, minus 2 times minus 103.8. Now I think it looks like it should be better. 6 times minus 393 plus 8 times minus 241.8 minus 2 times a minus 103.8. That looks better. Yes. So I get my answer. I'm coming out with minus 4087.8, and units are kilojoules. Remember, each one of these is kilojoules per mole times the number of moles. So it's going to be kilojoules for the reaction the way it's written. And if I round off to 4 significant digits, I get minus 4088 kilojoules. And that is response D, so we're good. All right. I need to go back to here again. Yes. Yeah. And now I'm ready for number 21. Okay. Now, this one, I think we can do without going to the pad. We can look at the reaction, and I think we can get the answer. If this reaction is carried out in a rigid, constant volume container, and it's thermally insulated so that heat can't get out, then what would happen to the pressure? Would it go up or down? Well, let's look at this. It says one of the questions is the pressure would increase. Well, would it or not? I'm going from 7 moles of gas, 7 plus 2 is 9 moles of gas in the reactants. I'm going to now 6 plus 8 is 14 moles. So I'm increasing the number of moles inside the container. That's going to cause the pressure to go up. P equals nRT over V. So the number of moles goes up, the pressure is going to go up. So statement number 1 is definitely true. The temperature inside that system, is it going to go up or down? Well, we just saw it was exothermic by a big number. So the temperature will also increase. So both statement 1 and 2 are true. So that one we don't have to really do any calculations on. Now, suppose that had been liquid water. How would that have changed things? Well, I went from 9 moles of gas to 6. So the pressure would have gone down. Now it's still exothermic, so the temperature would have gone up. But if this had been liquid water, only statement 2 would have been true. So it would be C instead of B. All right, now let's look at this. How much heat is involved when 1 liter of oxygen gas is used to burn benzene at 1 atmosphere pressure and 25 degrees? So, okay, now this is going to be a stoichiometry problem. So I do need the pad for that. Okay, so how much heat is involved? Well, we calculated the heat flow already. And we're going to go from, we're talking about oxygen. So if I take 15 O2 gas, that is going to, with the appropriate amount of propane, that's going to produce, or it's going to give me 4088 kilojoules come out. Now, I want to know how much for 1 volume equals 1 liter at what temperature are we at? 1 atmosphere pressure is equal to 1 atmosphere, and the temperature, T, is equal to 298.15. So I need the number of moles. So if I put the number of moles up here and 15 here, and I want to know then, I need to get the number of moles. So number of moles is my sidebar. The equation is showing 15 moles, just to complete what we're doing. It's going to be P times V over R and T. Number of moles. Pressure is 1 atmosphere. That's in the correct unit. Volume is 1.5 liters. That's good. R is 0.0821. And the temperature we said was 298.15. Okay, so that divided by that and that will give me my answer. So 1.5 divided by 0.0821 and divided by 298.15 is my number of moles, N, is going to be equal to 0.06127 and some more digits. Okay, so that's my number of moles. Okay, now I'm ready to do my rebalancing factor. The rebalancing factor is going to be N, which I just calculated. The equation quantity is showing 15 moles. And my answer, the heat, is going to be that N divided by 15 and multiplied by the heat flow in the reaction, minus 4088 kilojoules. So I'm ready to do my math. Okay, so the number I've got on my screen is N. I want to divide that by 15. Divide it by 15. Then I want to multiply it by minus 4088. Yes. And I'm coming out with the wrong answer. Oh, I see.
Over the wrong.
I gave you a different heat. Okay. All right. I guess you can figure out why I did that. I didn't want to give you the answer to the other problem. Okay, my heat was supposed to be minus 43.94. So I need to back up and punt. So 0.06127 92284 times the heat I gave you in the problem was 4394. And divide that by 15. I haven't done that. Okay, so when I do this, I come up now with the answer of 17.9507 in digits. That would round off to 17.8, and that is, I'm sorry, 18.0. Evolved, it's negative, so that would be response C. And pause, screen share so you can see the choices I gave you too. See, I wanted you to understand that if it's negative, the heat is evolved. And it's an exothermic process. If it's positive, then this would have been the answer. Okay, now this one, number 23, is going to be another stoichiometry problem dealing with limiting reagents and heat flow. The heat problems, stoichiometry problems are really easy. I think you can see that. Because all I got to do is multiply my rebalancing factor by whatever the heat flow is. Okay, let's go aside and work this one. It's number 23. I want to use benzene, and it's showing 2C6H6. And I'm using oxygen, and it's showing 15 O2s. And the heat flow, I'm going to read what it actually says, is minus 4394 kilojoules for the reaction. Now the problem says I have 1 mole here, and it says I have 5 moles here. The equation is showing 2 moles of the propane and showing 15 moles of O2. So there are my 2 rebalancing factors. It's going to be this one divided by 2, so that's going to be 0.5, 1/2. I can even divide by 2. What about that? I'd rather divide by 1. Okay. And then 5 divided by 15, I think that's going to be 1/3. So that's going to be 0.333 repeating decimals. Okay, so again, this is smaller, so this is my limiting reagent. My answer is going to be equal to the rebalancing factor, which we got there, multiplied by the heat, which we have up there, minus 4394 kilojoules. And so let's do the math. So I'm going to take 1 and divide, well, go ahead, 5 divided by 15. I know what that's going to be. It did come out that right? And then times minus 4394. And I'm coming out with minus 1464.6666. So 1465, which should 1465. 2 no decimal places like the answers are showing. And well, it says 1464 evolved and 1465 absorbed. I think I got a little typo right there. They should both be 1464, but it's evolved, and that's B. But I don't think no. And times 4394. You know, I've typed it in correctly. I think this answer should have been 1465. That would have matched the answer below it anyhow. That's probably right. Okay. All right, now. 25. Let's go back so you can see the questions again. Okay. Number 24 is to, it's a heat flow problem. So we're going to need to use heat gained equals heat lost. So let's go back and take a look at the camera, and let's work number 24. And what I'm going to say is mass times specific heat times delta T of the hot object, that's the heat flow, is going to be equal to the mass times the specific heat times delta T for the colder. So let's just identify what we got. The hot one is going to be the copper. The mass of copper is 50.0 grams. The specific heat of the copper is what we're asked to calculate. Yes. So this we don't know. Now the temperature change. The copper is going to start out at 100 degrees. That's going to be my high temperature limit. And it's going to go down to some temperature T. And we're going to know that answer, but I'm just going to put that number in. This is going to be the thing we have to calculate. Mass of the water. Well, we got 250 grams of water. The specific heat of water is okay. Let's look at this a little bit more carefully here. All right. I'm given the molar heat capacity of, no, I'm asked to calculate the final temperature. I'm given these data. And I want the specific heat of water. Now, the temperature of the water is going to go up to that temperature T, and it started out at 1.5. So I want to subtract off 1.5. I'll get everything over here a little better when I recopy it. But I'm seeing, I think I'm going to need to do some conversions, because there's two different ways to handle this problem. The specific heats are given in joules per mole per degree instead of joules per gram per degree that I expected. And they're both like that. Now, there would be two approaches. I could take the 50 grams and convert it to moles of copper. And I could take the 250 grams and convert to moles of water. And maybe I'll do that. So I'm going to take this 50 grams of copper, and I'm going to convert it from grams to moles. 1 mole. And for copper, it's 60 something. 63, is it? Point something or other. Let's take a look. Copper, 63.546, 63.55, I guess, be okay. 63.55. Now, that gets me moles. So now let's put the specific heat for copper that was given in moles. That's 24.4. And that's going to be in joules per mole. And at this stage, per degree. And then I need the temperature change. The temperature change for the water was 100 minus T. And now that's going to be equal to what I get for the water value. The water, I've got 250 grams. 250 grams of water. And I want to convert that from grams to moles. 1 mole of water is 18.02 grams. Now, I've got this now in moles. The specific heat was given in moles for water was 75.3. And the temperature change in water, it started out at 1.5. And it went up to the temperature T. Now I'm setting this up this way because what I've got on the left-hand side automatically, always and forever, will be positive, because that number is bigger than that number. There's no way I'm going to get a negative value in this subtraction. Same thing is true down here. That T is always going to be greater than 1.5. So this is going to be positive. I've set this up so that I don't have to have a minus. Now your textbook's going to tell you one of these numbers is negative out front and you put final minus initial, so they would have turned the this one around and had a negative sign out there in front of it. Well, I don't like to do that because it's too easy to make that mistake, especially with a calculation this complex. You're going to see what we got to do here in just a minute. So let's go ahead and do it. I'm going to take this, divide by this, and multiply by 24. And then I'm going to multiply it by 100. And then I'm going to subtract 1 times this times, So I'm going to do that calculation once, and then I'm going to write down the numbers that I get. So I take the 50. I want to divide that by 63.55 and multiply it by 24.4. Okay, so 50 divided by 63.55 times 24.4. That's correct. So what I'm coming out with when I take this times this times this is 19, and that's going to be the multiplier right there. So I'm going to have minus 19.1974823 is all my digits. And now I'm going to multiply that by 100 to get the other number, times 100. And I get 1919 point, just copy off that, 748, and the other digits is 23, but and this one was times t. Okay, so I've got this number minus that many t on the left. Now let's do the right hand side. 250 divided by 18.02 times 75.3. 250 times 75.3. Yes. And divided by 18.02 gives me 1044.672586. And now that's times t. And now I'm going to subtract off 1.5 times that, times 1.5. And I get minus 1567.008889. Now, once you look at the math, this number is negative. I can add it to both sides. So that'll get rid of it here. So I'm going to add 1567.008879 to that number. And then I'm going to add plus 19.19748 t to both sides. So that means this will disappear. And over here, I'm going to add plus 19.1974823t. Now, when I'm done, I'll get this and this plus this equal to each other. So I've got this. No, I've got that number. I've got that number on my screen. Wait, what have I got on my screen? I did this times 1.5. So I've got 1567. I've got this number here on my screen that I'm adding to this number over here. So I'm going to do that right now. Plus 1919.74823 was the other digit, just to have everything done. Now, when I've done that, I'm coming out with 191976,390. That doesn't look right to me. Oh, I know what I did wrong. I didn't put my decimal point in up there. Okay, back up and punt. 1567.008879 plus. Now I want my 1919.7 That's a 4. 4, 8. 4, 8. 2, 3 was the other digit. That's got it. Now, that gives me a number that makes more sense. I get 3, 4, 8, 6, 7, 5. I don't want that one. Okay, 7, 5, 7, 109. And now this is a number, and I want to add now the 1919.74823 to this number up here, 1044. So I've just got to enter all of these numbers, 1044.672586, I think, hard to read my own writing, plus 19.1974823 T. So what I'm coming out with now is 1063.870068 T. I want to divide both sides by that same number. Okay, and that's going to give me the value of T. So I want to take this number, 3486.75109. I want to divide it by the answer. And I'm getting T, this comes out to be 3.277421 and some more digits, but to 2 decimal places, it's 3.28. Now let's see if this makes sense to us. The temperature has to be between 100 and 1.5. It is. Now, it's closer to the 1.5 than it is to the 100. Shouldn't it be? Yes. We had a lot more water than we had copper, and the heat capacity of water is, I guess, close to twice, almost 3 times the heat capacity of water. The water is about 3 times the heat capacity of copper. So it's going to keep the temperature closest to the temperature of the water. And that does make sense. And if we go to number 24, the answer is A. So we're good with that. Okay, so let's go back and look again. And let's work out the remaining questions. Using the bond dissociation energies on the data page, estimate the energy of this reaction. So let's go do that. Okay, and now number 25. That's all right. We're going to do a bond dissociation energy, and we got CH4. So we're going to know how it's bonded. CH4, carbon needs 4 bonds and hydrogen needs 1. So that has to be the bonding structure of CH4, and I've got 1 of them in the reaction. I'm going to react that with Cl2. Chlorine's in group 7. It forms 1 bond with 3 lone pairs, and I'm just interested in the bond. So it's Cl2. So these are my reactants. The product that I'm going to make is CH, H, Cl plus HCl. Okay. Now, if I'm looking at this, here's what I'm going to make. I'm going to make myself a table. I'm going to put the reactant bonds here and the product bonds over here. Now I'm going to remind myself that these are going to be negative energies. Dissociation energies are all given in the table as positive numbers. So let's count up our bonds in each type. I've got 1, 2, 3, 4. I've got 4 C to H or H to C single bonds. And I've got 1 C to Cl to Cl bond in this one. In the product side over here, what do I have? I've got 1, 2, 3 CH bonds, CH single bonds, and I've got 1 C to Cl bond, and I've got 1 H to Cl bond. Okay, so there are all my bonds. So now let's go to our heat of formation table, and I'll need to screen share with you so that you can watch me get that. Let's go to that data table we had up here. Where is it? There they are. Okay. Okay, now the CH bond is, or H to C bond is this one, 414, and I got 4 of them. So it's 4 times 414. Should have planned better. I've got 1 Cl to Cl bond, and let's see where that is. There it is down at the bottom. No, yeah, next to the bottom. And that is 1, and the value is 243. 243. Okay, 3C to CH bond, so that's 3, and it's 414. I should have saved myself more room. I've got 1 C to Cl bond. There it is at the very bottom, 331. And 1 H to Cl bond. It must be up here somewhere at the top. There it is. H to Cl is 431. And I'm kind of curious to be sure I didn't copy that wrong. 331 to 431. Okay, that's good. All right, let's add these values together. And I'm going to have 4 times 414. Clear. 4 times 414 plus 1 times 243. 243. Okay, on the left hand, on the reactant side, I've got a total of 1899 joules involved in all of these bonds. Well, it's kilojoules, I guess it is. Kilojoules. Now, over here, I need 3 times the 414, so it's 3 times 414. Plus, I'm going to add the 331 plus 331 plus 431. And over here, I'm coming out with a total of 2004 kilojoules involved in this. Now, this sign is negative and this one is positive, breaking bond.
Can you share your screen, please?
Yes, thank you. Thank you. I will do that. So here are my numbers. We had 4 times 414, and we had 1 times 243. I added those together. I got 1899 kilojoules of energy in the reactants. And that energy, to break those bonds in the reactants, would cost you energy. You'd have to put energy in to do that. I had 3 times 413, 414 again for the carbon hydrogen bonds. and I would have one carbon chlorine bond is 331 and one hydrogen Cl bond is 431. So I add all that together, I get 2004 kilojoules in the product bonds. These are being formed, that liberates energy when you give off a bond. I want to address a point here that you might bump into when you hear this same discussion perhaps in a biology class. Biologists, what they say is exactly true, but the connotation that they give is absolutely wrong. They talk about in the bonds that make up your food, they are high energy bonds. Okay, high meaning nearer to zero. That's the truth of the matter. The bonds of carbon dioxide and water are much stronger bonds, but they talk about them being lower in energy, and that is true. They're more negative, further down toward zero. So what they imply is that when you take these high energy bonds in the food and you break them up, it gives you off energy. That's not true. It's when you break them up and reform the more stable bonds. So a bond in a molecule isn't like a little bottle with energy in it that you break open and the energy comes out. That's not what happens. That's sort of the implication that a lot of biologists use. And what they're saying is absolutely true, that the energy of the bonds in your food molecules are higher energies, closer to zero, than the product bonds you form, carbon dioxide and water. They're much more negative. So when you do go from the high energy food bonds to the quote lower energy bonds in water and carbon dioxide, you do get a difference in energy. But it's mostly because you form the stronger bonds, less to deal with the food bonds. It's more the fact that you're going to some of the most stable molecules known are carbon dioxide and water. So when you go to those very stable products, that's where the energy comes out. Okay, but now back to this. All I got to do now is I've got my 2004 on my screen. I want to take 1899 and subtract the answer that I have on my screen, and I get the energy flow is minus 105 kilojoules. So that should be the answer. If I share screen, go back to here, go back to wherever we are, 25. Yes. And so we got an energy of minus 105. Now, I should have showed you something else while we're here. Let's, yeah, I'll go back to my screen to do that. I want you to notice something. If I've got 4 of these bonds on this side and 3 of these bonds on this side, I'm going to subtract them. So I can do it right here and save myself a little work and make that a 1. And sometimes that makes it a little easier. So if you took 1 times 414 plus 18 and add that together, that would give you a new heat here. And then you go over here and you just add these 2 numbers together. And then you subtract that one from your new heat value, you're still going to get this 105. So sometimes you can save yourself a little bit of effort. If you have the same bond, it's got to be exactly the same bond in both the reactants and the products. You can just eliminate it from the calculation. I wouldn't try to do it back up here. Now, sometimes here's what I'll do. And I see a carbon-hydrogen bond in the reactants, that one, and I see a carbon-hydrogen bond in the product, so I'll do that. I see another carbon-hydrogen in the reactant and another one in the product and another one in the reactant and another one in the product. Now, when I do that, I see I only need to use this one and this one in the reactants and this one and this one in the products. So it can save you a little bit of time, a little bit of effort, but I would be cautious in doing this. Once you do it and you practice and you're experienced, you probably can do it right. But when you X out a bond, it's got to look exactly like the same exact bond in both sides. So you've got to be a little careful when you do it that way, but that will still work. Okay, now let's go back. Okay, and we're getting closer. Number 26, another stoichiometry reaction, isn't it? Okay, now this one is a reaction, and we want to get delta H. Now, number 26, so we're getting delta E. All right, good, okay, good. I want to double checking to be sure we got the heat flow given, and we didn't have to calculate it some way or other. Okay, so now we're given this reaction, and it's 4NH3, and it is gaseous, and 5O2 gaseous goes to 4NO2, and it's gaseous. Uh-oh, watch out. Look at water. Plus 6H2O liquid. I'm going to put a big star there to watch out what I'm doing. We're told delta H is equal to minus 1166 kilojoules. And we're asked to see what is delta E. Okay, we need to remember the relationship. Delta H is E plus PV, so delta H is equal to delta E plus P delta V. We're at constant pressure, and that's going to be minus the work, okay? So, and that's going to be delta H, I have a number. It's minus 1166 kilojoules. That's equal to delta E, which I need to calculate. Now, P delta V is delta N plus delta N times RT, where delta N is the difference in the number of moles of gases. Okay, so delta N in this process is going to be equal to, I've got 4 moles of gas from here, and I've got 9 moles of gas on here. So 4 minus 9 is minus 5. Okay, so now I can do my calculation if I wanted to. Let's solve for delta E. Delta E is equal to delta H, which is minus 1166 kilojoules. And now this is a minus 5. So I'm going to take it across on the other side. It becomes plus 5 RT. Now, let's go ahead and set up 1 minus 1166. And this is 5 times R is 8.314. It's in joules now. We have to use a joule value. Times the temperature is 298.15, unless we're given a different temperature. It was. Okay. Now, here's what I wanted to do. 8.314 is joules per mole. This is in kilojoules. They have to be in the same unit. So what I'm going to do is I'm going to make this in joules, do the calculation, and then I'll get my answer for delta E in joules. If that's not the right one, I'll convert when I get there. So this is times 10 to the third. Now that's going to be joules plus 5 times that. So now let's do the math. So this number is positive. Remember, I had a negative 5, but it moved across to the other side. It becomes plus 5. So I've got times 8.314 times 298.15. Now that's the number for this side. I need to subtract off minus 1166 second exponent 3. Now, if I didn't screw things up terribly, I get minus 11,53605.905 joules. Now, I'm looking at the answer, it's in kilojoules. So I want to convert from joules to kilojoules. Kilo is 10 to the third. So I now want to divide that by 1,000. So I divide that by 1,000. And I come up with minus 1153.605905. And now this is in kilojoules now. And I'm going to round off the answers, have no decimal places, so we get minus 1154 kilojoules is our answer. And that is response D on the exam. So we're good. Watch out though, one of these other answers, I'm guessing, I don't know for sure, it's probably this one, is for including the water as a gas. So be sure, be very careful, and watch out for that tricky old Dr. Pearson.
So did you substitute the PV for delta nRT? Is that?
Yes, that's right. Yes. Way back up here. Yeah, you still seeing my screen. Way back up here, P delta V was delta nRT.
Okay.
Mm-hmm. So that's where we make that substitution so that I come out with energy units.
Gotcha.
And that's in energy units. And remember, you do have to have that value for R in the energy unit. Okay.
What would be different if water was a gas?
I'm sorry?
What would be different if the water was the gas instead of the liquid?
Yeah, if it were a liquid, the only thing that would change is we've got 10 moles of gas here and 9 over here. So delta N would have been +1 instead of -5. And that's probably about enough to make this difference in the heat flow.
Okay, thank you.
Mm-hmm. All right, let's see, we're still looking over there. I need to show you the exam and work through the last problem on the practice exam. Calculate the work done in this reaction. It's the same reaction as above. So I can take a shortcut here if you'll allow me, because I've already have delta H. That was given in the problem. It's minus 1166 kilojoules. And I already have delta E. We just calculated it. So if we're confident we got it right, it's minus 1154 kilojoules. So delta H, remember, is delta E, plus P delta V is minus work. So solving for work, put it over here, work would be equal to delta E.
Did you switch your camera?
Oh, you're not seeing what I'm doing. I'm sorry. Okay, all right. Now, let's look again. There we go. We had delta H given in the problem. Delta E we did in number 26. And delta H is delta E minus P delta V. And P delta V is work. So this is minus the work. Now I solve for work. Moving across over here becomes positive. and moving delta H over here, it becomes negative. And now all I have to do is put the numbers in. The number I got for delta E was minus 1154 minus the value given in delta for delta H was minus 1166, and that's kilojoules would be the unit again. So if I subtract those off, this minus times that minus is positive. So I'm going to take that number and subtract that one. So I take the 1166 minus 1154 gives me plus 12 kilojoules. Now when I'm calculating work, I'm going to ask myself, does this really make sense for the sign? Okay, let's look back at this reaction. I had 9 moles of gas going to, I had 9 moles of gas. I've got a container that's got 9 moles of gas in it. And in the products, how many moles of gas do I have? Well, I've got just 5 gas. Even remember the water's a liquid. I'm sorry, I've got 4. So I've got a container now that's only got 4 moles in it. So the volume would go down like that, wouldn't it? Now I'm looking at that picture and I'm seeing that in getting from the initial state to the final state, the piston had to go in. So the atmosphere pushed in on the piston, meaning the work went into the system. Anything going into the system is positive. So if I made a screw up and put the signs in backwards over here, I would have got the negative 12. But by making that comparison, I know it's not the negative, it's the positive value, because there had to be work done on this system because it went to a smaller volume in the products than it started out as in the reactants. So that's always check your units, check the sign, and check to see if the answer makes sense. Okay? And if I had come out with joules here when both delta E and delta H were kilojoules, I'd think something's wrong. And now there is another way to work this, of course. You can go back to this expression. You're still watching me. Work is minus P delta V. And so that's a minus delta N RT. And I could have then put the minus 5. 4 minus 9 is minus 5, and then times RT. And I could put this in, I would have gotten plus, which is in agreement with the sign we thought we should get, 1.5 times 8.314 times 298.15 would come out to be 12,000 joules, which you would have converted to kilojoules and get the correct answer. Okay.
Dr.
So,
Pierce,
yes.
is that a negative 1,159 minus negative 1,166? Is that what the numbers are?
Well, here's the two numbers. You're still looking at my screen, my paper. Here's the two numbers. This one's negative. We're subtracting a negative. So this times this is going to be a positive value. So the way I always do that is I do that analysis first. And then if I've got a positive, I put the positive in and then subtract the negative value. That way I only have to do one calculation. But if you put in on your calculator minus 1154, subtraction minus, little minus 1166, you're still going to get the same answer. But I try to avoid minus a minus like the plague if I can, because I tend to screw that up. I mean, if you put if you reverse these two, if you put the little minus here and the subtraction minus here, your calculator is going to go, oops, can't do that.
Yeah. So
And so I just do that analysis beforehand. If I've got a bunch of numbers strung together, I'm going to add together with a sign. I'm going to look for all the ones that are positive. I'm going to add all of those up first. And then I'm going to push equal. And then I'm going to subtract off all of the ones that are negative. And so again, like in delta H of products minus reactants, you could have a bunch of things, positive and negative, on each side of that equation. What I'm going to do is set them up so that I got my numbers on my paper. And then I'm going to look at all the ones that are positive first. And then I'm going to add all them together. And then I'm going to subtract all of the ones that are negative. I'm not going to add up all the positive ones and write that down. Add up all the negatives, write that down with a negative sign, and then do that subtraction. That just takes too much time, and it's wasteful. So I'm trying to impress on you how to maximize your time. Now, I will tell you right now, this is going to be the longest test you've had all year. So take as many shortcuts as you can. And again, here's what I'm going to do. I'm going to look at the test. I'm going to read through it first. There was some questions on here I could get just by looking at them. Remember, there were several up there. Got some process that did some stuff. I don't remember what it was. It was the heat and the reaction. Yeah, these questions, 15. I mean, this one, I could have read that question and said, well, the answer is 72, minus 72. I could do that one right away. And I could look at the next one. I could do the same sort of thing. I know that's the difference between these two numbers. So I could be a little careful to make sure I get the sign right, because that seems to be important here. So I could do that one really quickly. And then this one was, it looks like, yeah, just a read off. And I got that answer. So these 4 questions I would do on that first pass through and make sure I got those answers right. And then I'd go back and work the problems again. On my second pass, I'm going to go through and I'll start back up here at number 1. I'll look at that and say, yeah, I know how to do that one. And I can do it pretty quickly. I'm going to take 1,000 times this, and that's going to give me the number of grams. I'm going to figure the molecular weight, and I'm going to divide by 0.1 liters, and that's going to give me the answer. So I can look at this one. I immediately know how to answer it, and I would probably do that one on the next pass. I'm looking at this one. This is very similar to what we've done multiple times before. I would go ahead and work that one. This one, I can work that one pretty quickly too. And so I'm doing second pass, I'm doing 1, 2, and 3 for sure. Now this one, it's a limiting reagent stoichiometry problem. I know how to do it. It's going to take me some time. I've got to do them. So I may just go ahead and bite the bullet and do this one because I've already looked through and picked out the low-hanging fruit. And so I'm probably going to work these all together because I'm thinking about them in that order. Now, I don't think, I think yours will probably be in that particular order, but I do have scrambled versions of my exams, and whichever one I pull, I might pull one that's got these scrambled around in the test. If I do, and I see, okay, when I went through at first, I found some stoichiometry problems up here, and I found some more down here. Well, I'm going to do the ones up here, then I'm going to jump down there and do the ones down there. So I'm working all of these while I'm thinking about stoichiometry and so forth. You see, be smart and be wise in the way you take exams, and save the ones that you have trouble with till last. Now, what if you work one and you don't get the right answer? I'm going to just make a notation. I need to work number 25 again. I'm not going to go back and look for my mistakes. That takes too long. I'm going to do that when I have extra time at the end. So if I get to the end and I still got time, then I'm going to go back. But if I saw number 18 was one that I skipped, I'm just going to go back and look at 18, and I'm going to say, eeny, meeny, miny, mo, I don't know what. I'm just going to make a guess. Is it number 1, heads or tails? I don't know. I'm just going to guess. Eliminate the ones I know are wrong. And sometimes I can recognize a sign is not right in some of the answers. I can eliminate those bad signs. And then maybe I could recognize the numbers out of range. It should not be that big or should not be that small. So if I can see that, then I'll eliminate them. And once I'm through with the elimination process, instead of guessing 1 out of 4 chances, maybe I could eliminate 2 of the answers and I've got a 50-50 chance of getting it right. So then I'm just going to guess one of those 2. Again, I'm probably not going to go back and rework the problems that I didn't find a correct answer until I know that that's free time. I've got everything else answered except those. Then I go back and do those. And that'll be the wisest use of your time. Okay, all right. I think we're done with that. And I'm going to turn the recording off